The early history of astronomy is very fascinating because it gives the background of everything that we know today and how it originally got started. Okay. So, the earliest times, astronomy and astrology were pretty much the same thing. In fact, some people still confuse it, and I get calls and emails all the time wanting to know about the astrology meetings. One time we accidentally, I guess the newspaper screwed it up and put in that we were having a short course on astrology. And we had hundreds of people there standing around the corners of the room and hanging from the ceilings. And they all left at the break. And we never saw them again, but astrology brings them out. The sun, moon, and planets were thought to have mystical powers. And some people still think that. They read the horoscope in the paper and see what it is they're supposed to do based on the positions of the sun, moon, and planets. The planets were named after various gods and or vice versa, and in some cases the planets were actually the gods of that civilization. Gradually, more educated people began to seek more scientific explanations for what they would see in the sky, which is sort of like what you all are doing this evening. And this effort began about 500 BC with Pythagoras. Now, this is a remarkable date because in all the time human beings have been around, it's only been in the last 2,500 years that we've really made any concerted effort to figure out the universe around us. So 2,500 years ago was when this all got started. Here's Pythagoras. He's known to most high school students as the originator of the Pythagorean Theorem dealing with the sides and hypotenuse of right triangles. He believed and taught that the earth was a sphere at the center of the universe and that the universe itself consisted of concentric spheres in different layers, transparent or translucent so that the light from other objects could shine through. He referred to them as crystalline spheres. And he realized that the orbit of the moon was inclined to the equator of the earth because it moves farther north sometimes, farther south other times, so he was on to that. And he was one of the first to realize that Venus, when it appeared as an evening star, was not the same, or it was the same planet as appeared in the morning. The Greeks before then had two different names for it. Hesperus in the evening and Aurora in the morning. They thought it was two different planets. You'd kind of think they would be onto it that just right after one of them disappeared, the other one would appear in the other twilight, and then when that disappeared, the other one would come back again. But he figured out that it was the same one. Aristotle, we've heard of him for philosophy mainly, but he was also a scientist. Notice, by the way, this struck me looking at these pictures, these guys have really big heads, presumably full of brains, which is why we still remember them. So there's Aristotle. He correctly explained the phases of the moon and eclipses, which Bill Wilson did a couple of months ago for us. That's been known since the time of Aristotle, the information that he gave us then. He figured out that the earth was a sphere based on the curved shape of the earth's shadow on the moon when we had an eclipse of the full moon. You can see the earth's shadow moving across the moon, and it's curved, so he figured that the earth was a sphere. He also figured out that when you go farther north on the earth, you see more stars in the north and some go below the southern horizon, and vice versa when you move around. Sort of like what we were talking about several months ago on the sky and the earth. He noticed that and figured that must be due to the fact that the earth was a sphere. He had one more piece of evidence, and that was that the when ships would come into harbor, you could see the masts gradually coming up above the horizon as they would get closer. And so from that, he figured out that the Earth must be curved, spherical. He considered the possibility that the Earth rotated on its axis and revolved around the sun, which is, of course, what we believe today. But he ruled it out because of the lack of observable stellar parallax. Now, what does that mean? If the Earth were to go around the sun, the stars should move back and forth a little bit during the year, the nearer ones moving more than the farther ones. Sort of like if you hold your finger out in front of your nose and alternately close one eye and the other, you'll see your finger moving back and forth, or appearing to. And if you hold it out farther at arm's length, it moves back and forth a little less. Well, we don't see that with the stars. So sometimes we kind of come down on Aristotle for missing the obvious here, that the Earth does in fact rotate and revolve around the sun, but you can't be too hard on him because you really don't see any observable parallax. The way he worded it was the stars would have to be unimaginably far away for this to be true. And as a result of that, he ruled it out. Now just think for a minute about how far away the stars are compared to the sun. You know, if the distance from the Earth to the sun is our baseline, the Earth's orbit, how much farther away are the stars in terms of that? Well, the nearest star, Alpha Centauri, is 250,000 times farther away than the sun. And he couldn't even see it from Greece. He missed Sirius and Procyon, which are close enough to have a little tiny bit of parallax, but all the rest of the stars visible to the naked eye, there are only about 3 or 4 that are within 1,000,000 times as far away as the sun. The idea of the flat Earth, and it's not entirely over yet. There's a Flat Earth Society in England that have a few hangers on that still, and they explain away the astronauts' pictures and all of that in interesting ways. But that used to be the prevailing idea because it looks flat. And the Bible refers to the ends of the earth and things like that. So, you know, they're older ideas. You know, when we have these dates in here, that's when the discoveries and formulations were made. You know, not everybody catches on right away, and so there are always hangers on of the old theory. And like I said, there's still some today. Okay. I should mention, we'll get to this next month, but the parallax, or zipping back and forth of stars, for Alpha Centauri is less than 1 second of arc. Now the moon is 30 minutes of arc. A second is a 60th of a minute. And no star has a parallax that big. So you can excuse them for not being aware of the parallax of stars. At the very end tonight, we'll get to the first measurements of that. Here's Aristotle's Cosmology, which is, interestingly, this particular book was in French, but this shows the earth and water and air and fire, and then the moon and Mercury and Venus and the sun, and then Mars, Jupiter, Saturn, and the firmament of the stars around the most distant part. Probably not to scale, but at least kind of gets the order of things more or less correct. Aristarchus, another great astronomer. He made the first attempt to measure the scale of the sun, earth, moon system. See how close each one was with respect to the other. He used lunar observations, and we'll get to this more next month, geometry of lunar eclipses and phases to try to figure this out. Unfortunately, he was doomed from the start by inaccurate data because some of these angles are so very close to 90 degrees or 0 degrees that it's not possible to get a good fix on the measurement. So he was way, way off. However, his methods were flawless. He thought everything through carefully, he just had bad data. So his methods were later on used successfully by others. And we'll have more of that next month. He also proved that the sun was much larger than the earth, and as a result, he was one of the first to really promote the idea that the earth went around the sun. It just seemed to him that it wouldn't be reasonable for a bigger earth, a bigger sun to go around a smaller earth. That wouldn't make sense to him or to us now. So he first was one of the first to come up with the heliocentric or sun-centered model of the solar system. And he also said that the stellar parallax is not observable because the stars are extremely far away. So Aristotle set it up. It's either like this or like that. Aristotle went with one of them, and Aristarchus went with the other. Turns out Aristarchus was right. Eratosthenes, another one of the good ones with a nice big brain. He made the first attempt to measure the diameter of the earth, and he was successful. Within a few percent of the currently accepted values, he actually did determine the diameter of the earth. And we'll again get to that next time. Hipparchus of Rhodes, just right up here on North Parkway. He was interesting nose, greatest astronomer in the BC era. He was born in Nicaea, carried out most of his work at Rhodes and possibly in Alexandria, and he compiled a catalog of 850 stars, including their magnitudes and celestial coordinates. Now wait a minute, how did he come up with magnitudes and celestial coordinates? Well, he had to invent the magnitude scale and the celestial coordinate system, and then he was able to record his 850 stars using that information and the scales that he just developed. While he was recording the positions of stars carefully and remeasuring them over his lifetime, he noticed that they were moving a little bit and the celestial coordinate system was shifting. So he inadvertently discovered precession, the 26,000 year precession cycle that we were going over in February, and it's on the website if you want to do that. I'm not going to review that tonight, but it's a wobbling of the Earth's axis where the North Star changes and the intersection point of the celestial equator and the sun's path changes. So all the coordinate system gradually shifts over time, and he discovered that. He refined Aristarchus' calculations using better data and came up with the distance to the moon of 59 Earth radii, where the correct value today is 60. So that was getting pretty good. Still, before the time of Christ, we knew the ratio of the distance to the moon in terms of the diameter of the Earth. So that was an amazing accomplishment. He explained the different lengths of the seasons by showing that the sun was offset from the center of the Earth's orbit. Well, there's a little more to it than that, and we'll get to that when we get to Kepler later on. But he at least realized that the seasons were different lengths. The Aztecs and Incas and the others of that type didn't realize that the seasons were different lengths. They had them all marked off exactly the same during the 4 quadrants of the year. He determined the length of the year to within 6 minutes. Now that is a remarkable thing. Could we do that today? Well, if we looked up how he did it, we could. It's still possible, but I don't think any of us would imagine that you could determine the length of the year to within 6 minutes without any optical aid, no telescopes, nothing like that. He also set up the procedures for predicting eclipses. So they weren't just mysterious things that occurred out of the blue. And this was very useful to the priests and other clerics at the time, because if they knew when an eclipse was coming, they could frighten the bejeebers out of people by saying, if you don't reform, we're going to block out the sun. Well, okay, then it happened, and then 3 minutes later, okay, you repent, it comes back again. So that was very useful information for controlling the people. Ptolemy, with his Latin name Claudius Ptolemaeus, Now we're in the AD period, after the time of Christ. He was another Greek and Egyptian astronomer. They did a lot of traveling. He compiled the Almagest, the 13-volume encyclopedia that included everything that was known about astronomy up to then. The Almagest means the greatest, and at that point it was the greatest compilation of all of the astronomical knowledge. He included all the work of his predecessors as well as his own, but he didn't have a good footnote system and reference pages at the end, so it's not clear as to who did what and how much of his work was original or just worked in or just copied from others. We still don't know to this day and probably never will. But we owe a great debt to him for compiling all of what the ancients had already determined, and probably some on his own as well. He also confirmed Hipparchus's lunar distance of 59 Earth radii using an entirely different method of parallax. And again, we'll see that next month, the details. And he greatly refined the geocentric model of the solar system, the Earth-centered. You know, I don't know if you're all far enough into astronomy to realize that the planets not only generally move eastward along the ecliptic, but sometimes they stop and go backwards, and then they go forwards again. When they are at opposition, that is on the opposite side of the Earth from the sun, they go through a period of a couple of weeks usually, sometimes as much as a month, where their forward motion eastward stops and they go west for a while, sometimes in little loops, and then go back forward again. He explained that in terms of little circles built onto the orbits where the planet would come to this spot and then go into a circle and then proceed farther on. It made no physical sense, but that didn't bother anybody back then. But even he didn't believe it. He described them, but only considered it as a model for making predictions. He didn't really think that's the way the planets actually did, was moving on little tracks on top of tracks. This is sort of like any algorithm is not a real thing. There is not a thing floating out in the universe that says E equals mc squared. That's just a description of it. And his description of the motions of the objects in the solar system was such that you could use it for predicting the positions of the planets and eclipses and things, but he didn't think it was real. But others who weren't into the fine points of things thought the planets actually did that. He's also, here's the other side, the dark side of Ptolemy. He compiled the Bible, or 4 books of astrology, which is still considered authoritative by astrologers today. So, like I said, the distinction between astronomy and astrology was not as clear as it is today, and it still isn't for everybody. So the Ptolemaic model was considered infallible until the Copernican revolution, like 1,500 years later. Last month, we saw that it was remarkable that the Laplace nebula hypothesis lasted pretty much unchanged for 150 years. This lasted 10 times that long before it was seriously challenged. So as bad as it was endurable. Here's the model, kind of a fuzzy picture, but it shows the Earth in the center and the orbits of the planets around the Earth, and then the sphere of the distant stars out at the edges of things. Now, jumping ahead 1,500 years to Copernicus. Whoops. He was born in Poland, so I guess you could call him the celestial Pole if you wanted to. He was trained in law and medicine to start off with, and then became a canon in the Catholic Church. Not quite at the level of a priest, but he wasn't one of their big guns, so to speak, just a canon. He studied astronomy. It is Friday. It is Friday. He studied astronomy and mathematics extensively and became an authority in those fields. And by 1515, when he was still fairly young, he was convinced that the solar system had the sun in the center rather than the Earth. But he kept that a secret from his friends because he was afraid of what the church might do to him. He was a canon in the church, but the church had a lot of temporal power back then, and they kind of interfered in a lot of matters that you wouldn't think were any of their business, including theories of scientists. If you said something that disagreed with their theory, you could wind up in trouble. So the church, here's kind of a hoot actually, the church had aligned itself with the geocentric theory of Aristotle, who was a pagan, and they were against the theory of one of their own canons, Copernicus. And then it fell to a Lutheran preacher, Andrew Osiander, who oversaw the publication of De Revolutionibus Orbium Celestium, about the revolutions of the celestial spheres. In 1543, which you might notice was the same year that Copernicus died, on his deathbed, he gave permission to Osiander to publish the great book that started the Copernican revolution. And here he had, as you can see, the sun in the middle and all of the planets and the moon going around the earth, all of these in the correct order as we understand the solar system today. He explained the retrograde motions of the outer planets, where they go backwards, in terms of a moving planet Earth. And as the Earth passes up the slower outer planets, which happens at opposition, when they're both on the same side of the sun, the Earth's moving faster, so the outer planets look like they're going backwards. So like when you pass a car on the highway, it kind of looks like it's going backwards compared to you. And here's a diagram of that. Here's the sun, here's the Earth's orbit going around this way. Here's the orbit of Mars, also going around this way, but slower. So as the Earth passes up Mars at opposition, when they're both on the same side of the sun, it makes it look like in the sky that over here Mars was going forwards along the ecliptic, but then it goes backwards for a time and then forwards again. So it became a whole lot simpler if you let the Earth move around instead of being still and the planets going around on mysterious little circles on top of circles. The problem with that was it made the Earth into any other astronomical body, no longer the special center of the universe. It was just another planet. And of course, he was afraid that would get him into trouble. Well, he didn't get into trouble because he died right after the book was published. He also calculated the true sidereal periods of the planet's revolutions. Okay, what's the sidereal period? With respect to the stars, that's the true amount of time in the year of a particular planet, not just as seen from the Earth, but if you could take yourself away from that and see how long it takes the planet to make one complete revolution around the sun. That's the sidereal period or year of that planet. He was able to calculate that, of course, from observations made from the Earth, because that's where he was at the time. Okay. He also determined very accurately the distance of each planet from the sun, but only in terms of the Earth-Sun distance. So they were all multiples or fractions of the distance from the Earth to the sun, which we know is the astronomical unit. Remember that term? 93 million miles. We didn't know that then, but the Earth-Sun distance is known as one astronomical unit. So he made a scale model of the solar system, but the scale was unknown. It's sort of like having a map of Tennessee, but without a scale of miles at the bottom. You see that Nashville's twice as far away as Jackson, but you don't know how far away either one of them really is, just the ratio, and that's all he came up with. But that was, of course, a major accomplishment for Copernicus. So, the Copernican revolution, as it's referred to, had begun with Copernicus. Now we go to Tycho Brahe. He was Danish, and I'm not going to even say anything about a Great Dane, but he was born into a nobility family and apparently never wanted for anything. He started making astronomical observations when he was very young and observed a supernova in 1572. It's still on star maps as Tycho's star. And he showed that it had no parallax, which meant it was very far away. He had friends all over Europe who observed it And they all saw it in the same place in Cassiopeia. And had it been in the atmosphere, it would look like it was in a different place. No matter wherever you were, it would be somewhere else. But all of them saw it in exactly the same spot, which meant it was something way off in the heavens. So that broke down a major barrier, actually, that the idea that the heavens were immutable or unchanging fell by the wayside, because here was a brand new star as far as they knew. So that was a big deal. In 1576, King Friedrich of Denmark built him a royal observatory, Uraniborg, the heavenly mountain, on the Isle of Thane. And for 20 years, using non-optical instruments, because there weren't any at the time, just mechanical devices, he and his assistants made extremely accurate measurements of the positions of the stars and the motions of the planets, particularly Mars. They concentrated on Mars because it goes around the sun relatively rapidly, and you can get lots of data about many orbits. If you tried to do this on Saturn, where each orbit takes 29 years, it would have taken them a couple of lifetimes to come up with the same amount of data they got from Mars. Most of his measurements were accurate to within 1 minute of arc. Now remember, the moon is 30 minutes in diameter, so this is like a 30th of the diameter of the moon in the sky. All of his measurements were made that way. Well, how did he do it? Well, here is his observatory, the heavenly mountain, Uraniborg, and here's his mural quadrant. Mural on the wall, quadrant 90 degrees, and it's marked off in degrees and very carefully calibrated, and apparently they could sight out through the windows in the observatory and make measurements to within a very small fraction of a degree, like maybe a 30th or 60th of a degree. And here's another one, the sextant, 60-degree arc. It's all calibrated. All of these things are made out of wood and metal, and that was how he achieved all of his measurements. Like most scientists, he measured things over and over and over and over and over, and then took the average of the results, and that's how he got his results to be so accurate, rather than just relying on one particular measurement, which you can have an off day doing. It just all of the averages of years and years of work. He determined the length of the year to within 1 second. Remember, Hipparchus got it to 6 minutes, which was amazing enough. But here, still without any optical aid, got the length of the year to within 1 second. He proved that comets, same as the supernova business, were members of the solar system and not in the atmosphere. And unfortunately, he was kind of a jerk, and he ticked off the king and lost his grant. You can see, if you notice a little crease across his nose there, he one time got into a sword fight with somebody who cut off his nose, and he had to wear a little copper prosthetic nose for the rest of his life. So he was kind of a scrappy individual. But anyway, he lost his job, and for some reason, in 1597, when he had still 4 years left to live, he exiled himself to Prague. Now, if I got fired, I'm not sure where I'd go, but I don't think Prague would come to the top of my mind. But for some reason, that's where he exiled himself. And he took some of his instruments with him, and most of his observing records, for those of you who are familiar with the way science works, is a big no-no. Your lab notebooks stay with the lab. They belong to that organization. You don't take them with you. But he did. I don't guess he figured the king would know what to do with them anyway. And he spent the rest of his life, which was 4 more years, analyzing his data. He concluded, here's the important thing we've got from him, besides piles and piles of very accurate data. He said the planet's orbits can't be circles, that the data were inconsistent with that. So we're going to have to really give up on the circular orbits. Even if we allow the sun to be off-center in the circle, like Hipparchus had suggested, that still doesn't quite work out. So the sun is off-center, but it's not a circular orbit. He got that far. Also, he rejected the idea of a moving Earth. for two reasons. The usual one, no observable parallax. And secondly, he had some perceived biblical conflicts. He thought that if the Bible said the sun was rising, that meant that it was rising and not the earth was rotating. But as we see later on, as Galileo said, the Bible tells us how to go to heaven, not how the heavens go. But he didn't make that particular distinction and saw that there was a conflict there where there really wasn't. So he proposed a compromise, which was very ingenious. He had a stationary earth orbited by the moon and the sun. Well, the moon does orbit the earth, but the sun doesn't. But the other planets orbited the sun. So that was kind of a hybrid system. Mathematically, it's the same thing. We just have a different frame of reference. It's just only the frame of reference, the Earth's stationary rather than the sun. If you built a working model of the solar system with all the planets orbiting around the sun with little gears and stuff, and you picked it up by the Earth and held it still, you've got a Tychonic model of the solar system, because the Earth is stationary, the moon and sun would then be going around the Earth, and all the other planets would be going around the sun. So that was his version of it. It allowed for him to reconcile everything. Of course, it was wrong, but it made him feel better. So here it is, the Earth and the moon going around the Earth, the sun also going around the Earth, but with all the other planets and even a comet thrown in here going around the sun. So not too bad. Next we move on to Johannes Kepler. He was born in southwestern Germany and studied theology. A lot of these people start out on theology and then switch to medicine and then switch to astronomy. It's kind of you might want to think about that and the implications of it. While at the university, he decided that the Copernican heliocentric theory, sun-centered, was correct. And he became very proficient in mathematics and became a teacher at the university in Graz, which is now in Austria. But since he was a Protestant, the church forced him to give up his teaching position. Remember again, the church had a lot of temporal power back then, and so they made him give up his teaching position. So, once again, think I'll go to Prague. I got fired, so I'm going to Prague. And he became Tycho's observing assistant.
And it was a big cultural center at that time.
Yep.
Memphis was New York, right?
Yeah, that's right, yeah. Anyway, he wound up there and became the assistant. And can you imagine, Tycho has spent his whole life taking these observations, and he's getting near the end of his life, and he's struggling to figure out what all the data mean. And here's this upstart that comes in and says he can figure out all of those planetary data in 8 days. Can you imagine how that would gripe you if you were Tycho at the time? Well, it actually took him about 20 years, but he did it. So by then, Tycho was gone. He worked out a successful mathematical model to fit Tycho's data. Now in science, that's how you have to do things. If the theory doesn't match the data, the theory is wrong unless you know you've screwed up gathering the data. If you are confident that the data are correct, then the theory has to correctly explain that, or it's wrong and you have to tinker with it. So he figured out that first he tried all possible combinations of circles, including circles on top of circles and even further circles, and that didn't work out. He finally decided that elliptical orbits would be the only way to explain the data. So not only was Hipparchus right that the sun was off-center in the Earth's orbit, but he came up with the idea that it wasn't a circle but an ellipse. And again, he let his heart get in the way of his brain here. He was a numerologist and religious, and it took him a long time to give up on the idea of perfect circles, because that was ingrained in everybody that creation was perfect, so then the perfect geometric figure was a circle, no beginning, no end. So everything in the perfect creation had to be involved with circles. So that kind of messed him up for a while. Just a little bit about conic sections here. If you take a cone and you slice through it horizontally with a razor blade, what sort of cross section do you get? It'd be a circle, okay? If you slice through it, if you slice through it at an angle, you wind up with an elliptical cross section. If you slice through it where the blade is slicing down at parallel to one side of it, you'll wind up with a parabola. And if you slice vertical, now a cone is in two parts, right? It continues up the other way just as far as it goes down, which is infinite in all directions. If you take a vertical slice through it where it hits both sides of the cone, you get a family of parabolas. You get one down here and you get another one up there, a hyperbola, I should have said. So you have a set of hyperbolas if you do that. By the way, you can do this not with knives and snow cone things where you might hurt yourself, but you can do it with a lamp. If you get a table lamp with a cylindrical shade, you can aim it straight at the wall and get a circle. You can tilt it and get an ellipse. You can put it straight up and down and you get the hyperbolas. You can do all of this with, let the wall be your knife going through the cones of light coming out through the lampshade. You can draw an ellipse this way. An ellipse is defined as the locus of all points that are equidistant from 2 points. 1 point would be a circle. If we put these 2 push pins together, then we'd trace out a circle. You know, I'm not sure I would have done this on a woven placemat here, but anyway, if you do this with a loop of string and draw around it, you will generate an ellipse, and where the 2 push pins are the 2 foci of the ellipse. He also noticed, and this is very important from the Tycho's observations of Mars, that when the planet is closer to the sun, it moves faster than when it's farther away in the elliptical orbit. When it's at the other end, they slow down. So in 1609, he was still pretty young then, he published Astronomia Nova, the new astronomy. And he put these observations as his first 2 of his 3 laws of planetary motion. The first law is each planet revolves around the sun in an elliptical orbit with the sun occupying one focus of the ellipse. One time I had a student ask me, which focus? And although there's a general belief there's no such thing as a dumb question, I came to modify my view on that and just answered the left one. So, but here are your 2 push pins. The sun is one of them, and here's the elliptical orbit of the Earth with the sun at one focus of the ellipse. The second law is the planet orbiting the sun sweeps out equal areas during equal time intervals. Okay, what does this mean? When the planet is closer to the sun, it moves faster. Say this is a month. Out here, when it's farther away, it moves slower over that same month. However, since it's farther, the triangle has a longer radius than the one over here, and it works out that this area is the same as that area. Equal areas and equal lengths of time. So that's Kepler's second law of planetary motion. 10 years later, that was 1609, here at 1619, he published Harmonia Mundi, the harmony of the world, which at that time meant the whole universe. And he put in his third law of planetary motion, which is known as the harmonic law. The squares of the sidereal periods of the planets are directly proportional to the cubes of their average distances from the sun. Okay, what does that mean? First, just temporarily ignore the squares and cubes business. The sidereal periods, that's the year. The year of a planet is related to its distance from the sun. And the farther a planet is from the sun, the longer its year is. Jupiter's farther than the Earth. It takes 12 years to go around the sun. But it's not directly proportional. If so, if a planet were twice as far from the sun, it would have twice as long a year. It's not like that. If you take the year and square it, that's equal to the distance when it's cubed. And this is, if you express the sidereal period, or year, in Earth years and express the distance from the sun in astronomical units, then we come up with this very simple equation. P squared equals d cubed. The year squared equals the distance cubed. This is in Earth years, and that's in Earth distances, astronomical units. How do you remember which one is squared and which one is cubed? Well, period is time, or length of the year. So I think of time squared, like in New York. So time square gives us distance cubed. Later on, we'll see how we use that third law to determine the distance of a planet from the sun if all we know is its year, or vice versa. And that's useful for a lot of other things as well. All the values of the distance had to be expressed in astronomical units because that's where Copernicus left it, right? He just had a scale model but no scale. But that's fine because the way the equation is set up, that's what we want anyway, the period in Earth years and the distance in astronomical units. So that worked out fine. Question?
Also true for the Galilean satellites?
Yes. Absolutely. It's true for any object orbiting any other object. But, of course, Earth years don't go in there. In a few minutes, we'll see Newton's generalization of this. This was just for the solar system. Yeah, all of Kepler's laws apply just to the planets of the solar system and the sun as the central object. But the extension of it applies to everything, as we'll see shortly. He still wanted to find out the scale of the solar system, and he proposed using a transit of Venus. Remember, we've had one of those a couple of years ago where you could see Venus moving across the surface of the sun as it orbited around. Came between us and the sun directly, a little black dot moving across. It's true that if you set up the geometry of it, if you observe it from two different places on the Earth at the same time, you can do some triangulation and just see what the actual distance is if you know how far it is from your observing station to the other one. Then you can set up the triangles and calculate the distance to the sun. The problem was you didn't know when you were making your observation if it was the same time as somebody else, because clocks were not that good then. If you took a clock thousands of miles away, it could be several minutes off by the time you got there, and that would screw up the whole thing. So finally, 150 years later, that method was used after clocks were improved and Kepler's idea checked out. However, by then we had already done it by other means that we will get to shortly. Next we come to Galileo Galilei. He was probably the last great person to go by his first name until we got to Elvis and Madonna and ones like that. He was born in Pisa, Italy, where the Leaning Tower is. It was already there. In fact, he did some experiments using the Leaning Tower of Pisa. He started out in medicine, switched to mathematics, and became an expert in both fields, taught mathematics at universities in Pisa and Padua. And he became famous for his experiments and theories. He is known as the father of the scientific method because he not only had these great ideas floating around in his head, but he tested them out and did actual experiments, such as dropping two cannonballs of different size off of the top of the Tower of Pisa, and contrary to what everybody seemed to think would happen, they landed at the same time. And most of his experiments, he was during a boring sermon one day, he was watching the pendulum, or he was watching the hanging candle in the sacristy of his church swing back and forth, and noticed that it always took the same amount of time no matter how big a swing it had, and wound up inventing the pendulum clock as a result of that. We could spend the whole night on Galileo, but we can only look at some of his astronomical contributions. He put all of these into the form of equations, which, as I mentioned last month, equations are our friends. They let us list all of the relationships between the variables so we don't have to figure it out from scratch every time. We just plug into it and solve. In 1609, he heard of Lippershey's telescope in Holland. Lippershey was an optometrist, and or a glasses maker at any event, and he discovered that if you put certain lenses together, you could make a distant church steeple appear closer. Well, Galileo heard about this and decided this might be useful in astronomy. So he didn't invent the telescope, but he probably built the first ones that were used in astronomical work. In 1610, the next year, notice he didn't fool around, he published the Sidereus Nuncius, the News of the Stars, announcing some of his discoveries. He saw that Venus not only went through phases like the moon, but its size apparently changed as it was going through its phases. And that convincingly proved that Venus revolved around the sun rather than around the earth. We'll have a drawing of that in just a moment. He also discovered sunspots, and that proved that a major heavenly body was not perfect. That was another one of the ancient beliefs that was hard to give up, that all creation was perfect, and if the sun had zits on it, then it wasn't perfect. So sunspots showed that. He also showed the rotation of the sun by watching the sunspots go around the sun as it rotated. He also discovered star clusters. Although there's some reason, and we'll see at the second talk tonight, that Ptolemy probably discovered a star cluster in Scorpius, but he really went to town on the star clusters. Here are one of his drawings of the moon showing its craters compared to the actual ones that we see with a photograph of the moon through a telescope. Not too bad for the first drawings of the moon ever made. Yes?
For the rotation of sunspots, was there other knowledge that he had that made him realize the sun was rotating as opposed to the sunspots moving like clouds?
No, I don't think so. But when they would come back around again and then fade out, there's usually more than one way to explain something, and to him, the easier explanation was that the sun was rotating, that these were features on the surface of the sun, rather than, back then they didn't realize that it was gaseous, and it could have been clouds moving around it, but to him the better explanation would have been that it was actually rotating. And also it was always the same, the 28 days or whatever it is, hours and minutes, and that would be unlikely if it were weather patterns. So I'm sure he had good reasons documented. Okay, as we see Venus through a telescope, we see that it goes gibbous here, sometimes almost completely full, and then it gets to a thin crescent. But when it's a crescent, it's a lot bigger than when it's full. Now here's another perspective of that. Here's Venus kind of on the far side of the sun. As it moves up and then comes back down between us and the sun, we start seeing more of the dimly lit side of it, and it becomes a crescent, but very large because it's so much closer then. In fact, the last time we saw it when we were out observing last month, it was a crescent that just matched the crescent of the moon. At the same time, we could see them in the same field of view, and they both had the same shape for the same reason. Here's how it doesn't work. If Venus went around the Earth, it would go through phases because the sun's over here. We'd see crescent and full and so on, but it would stay the same size because it's in an orbit around the Earth. But that's not what we see. We see that since Venus is orbiting around the sun and the Earth's over here, that as it goes through the phases, as it gets more full, it's on the far side of the sun and gets smaller, and as it becomes a crescent, it gets larger because it's closer to us, because it isn't going around us, it's going around the sun. So that was a big verification of the Copernican heliocentric model of the solar system. Still 1610, the same year, Galileo published more results. Numerous stars too faint to be seen with the naked eye. Jupiter's system of moons. And here was another big no-no that just fell. The common thinking then was that if one object moved around another, it couldn't have anything moving around it. However, everybody believed that Jupiter moved around something, whether it was around the sun or around the earth. Either way, Jupiter was moving. And now he showed that its 4 bright moons moved around Jupiter from one night to the next. He recorded them and said it was like a little miniature solar system. But that got rid of that earlier theory that you couldn't have things orbiting around something that was orbiting. Kind of reminds me of Belloc's poem about fleas. Large fleas have smaller fleas upon their backs to bite them. These smaller fleas have lesser fleas, and so on ad infinitum. So you can have things orbiting around things that are orbiting. Also, he discovered that when he cranked up his telescope to the maximum 30 power, stars still like little points. They didn't magnify like the planets did. The planets, Jupiter, Saturn, Venus, would get bigger as he used higher magnifications. But the stars stayed as points, which he believed indicated that they were much farther away than the planets, which of course is true. He made a point of showing that all of his observations proved the Copernican theory and went against the church's Aristotelian and Ptolemaic dogma. He would even set up little observing sessions, outreach programs for the clerics in his area, and he would invite them over to look through his telescope and spent most of the time berating them for their stupidity in believing the old system. So he wasn't out to win friends or anything. He was pretty obnoxious. So in 1616, the church issued a decree prohibiting anyone from holding or defending the false and absurd Copernican theory. Now, this 1616. 1623, Galileo's good friend, Maffeo Barberini, became the Pope. And he figured that, well, my luck has changed. Now that my friend is the Pope, I can go ahead and do anything I want. Well, it didn't work out that way. The Pope stuck with the old Aristotle theory and didn't go along with Galileo's theories about the Copernican system being correct. Didn't work at all. Many years later, Galileo finally received the church's permission to publish the dialogue on the 2 great world systems, meaning the geocentric and heliocentric theories, the Aristotelian and Copernican theories. He set it up like a comic book with drawings in it that he made. And he had the dialogue between the wise person who was doing the Copernican theory, and of course that was him, and the other person who held to the other geocentric theory. He named Simplicio, or Simpleton, and he drew him to look just like the Pope. So that didn't go over well at all. So they called him before the Inquisition. They did not torture him. They just forced him to renounce his beliefs. But even as he was walking out, he kind of had his fingers crossed and said, "But the earth still moves." He just sort of muttered that. Some people say they heard it, but it's apocryphal. We don't know. But so he had to renounce his beliefs, which of course he didn't, and sentenced to house arrest for the rest of his life. In 1980, the church reopened the case, and only 9 years later, they exonerated Galileo. Now, you would think from that they would have learned not to mess around in scientific theories, but unfortunately, from recent events and proclamations, they have not learned that lesson. Okay, Isaac Newton, probably one of the greatest minds of all time, along with Einstein and Hawking. They've got to be the top 3 of all time. He was born in England shortly after Galileo died, so they didn't overlap any. He studied at Trinity College at Cambridge. College was hit by the plague and shut down for 2 years. Now, I don't know what you or I would have done if our college was shut down for 2 years, but probably would involve beer and girls, I don't know. But anyway, he used that time to work out most of his theories, ideas on mechanics and gravitation. And then he was later, after he graduated, appointed the Lucasian Professor of Mathematics at Cambridge. By the way, do you know who it is today? It's Hawking, yeah. 1684, Edmund Halle was discussing the inverse square law of gravitational attraction with Newton. So I guess they got together one Saturday afternoon, and after the football game, they decided to talk about the inverse square law of gravitational attraction. And Newton happened to just say that years earlier, he had shown that if there were an inverse square relationship between the objects attracting each other due to the force of gravity, that would lead to elliptical orbits of the planets, which Kepler had already shown was the case. So Halle got all excited and urged Newton to write up his work. Don't just let it fizzle out, write it up and publish it. So here's Edmund Halle. What do we mainly remember him for? Well, his comets. Well, he is renowned for that, but I think his greater contribution was getting Newton to publish his work. Sort of like Mendelssohn, for example. What do we remember him for? The insipid wedding march, probably. But what he really should be remembered for was resurrecting and popularizing the music of Bach. Had it faded out, but he dug up a trunk of it and used his orchestra to play it and got Bach back on the charts again. So same here with Halle. He had his own reputation for the comets, but he got Newton to publish. In fact, he was a member of the Royal Society and got them to publish it if Halle paid for it, which he did. So he published the Mathematical Principles of Natural Philosophy. What is natural philosophy? Well, that's what we call science today, natural philosophy. In the Principia, Newton stated his 3 laws of motion: that a body remains at rest or in uniform linear motion unless it's acted upon by some external force. That seems obvious to us today, but back then it wasn't. You needed the horses to keep pulling the carriage to keep it moving. He said that things would keep moving in a straight line if they weren't acted on by any other force. So the friction and everything else had to be worked into this later on. So that was his first law. The second law, the change in motion of a body, where it speeds up, slows down, or curves, is proportional to and in the direction of the force you impose on that, the F equals ma, second law of motion. And the third one, for every action there's an equal and opposite reaction, the principle behind rocket engines, among other things. He also set forth his law of universal gravitation, which described the force of gravity between any 2 objects. It could be the sun and the earth, it could be 2 stars in a star cluster. Any 2 things follow this rule. The force between them is equal to their masses multiplied together, divided by the distance between them squared. And that's the inverse square law that he and Halle had been talking about. Leads to elliptical orbits of the planets. The G is the gravitational constant. It gets the numbers and the units working out right, but it's a proportionality constant. So the force is proportional to the masses of the objects and the distance between them squared. Very simple equation, but it explains the whole motions of the solar system. In order to do this, in order to derive Kepler's laws, Newton had to invent calculus, which was also done about the same time by Leibniz in Germany, and we use the Leibniz notation for calculus today. Newton's was kind of clumsy, and he didn't think of it as being anything that would stand on its own. He just used that as a tool for the work that he was actually doing. After lengthy derivation, he not only produced Kepler's laws, but extended them to a more general situation. And they can be used for all kinds of things, calculating the masses of planets, binary star systems, even galaxies. Here's Newton's version of Kepler's third law. This is the way it shook out. The M is mass again, masses of the sun and the mass of a planet. And the period is still the year squared. The distance is here. are the distances of each object from the center of mass. In other words, as Mars orbits around the sun, not only does Mars move, but the sun ooches back and forth just a little bit as well, and around the center of mass of the two objects. And those are all in astronomical units again. And solar masses there. For a small planet like Mars, the mass of Mars is much less than the mass of the sun. So you can just drop that out. And the mass of the sun in solar masses is 1. So the left side is p squared again, just like Kepler's law. The sun doesn't move much when Mars orbits around it. So this is the distance of Mars from the sun, but this, or from the center of mass, but this is negligible, so you can drop that out. So what do you get? P squared equals d cubed again, which was the derivation and extension of Kepler's third law. Here's a thing I like to do is throw in a timeline. Here's Copernicus, Tycho, Kepler, Galileo, Newton, and Shakespeare, just for fun over here, Hamlet. Also, if you want, 1607, the founding of Jamestown, 1620, the Pilgrims land at Plymouth Rock, just a few other things going on in the world at the same time. The last two, we're on the last two now, folks. And you may not have heard of them. As important as they are, they're not household words. James Bradley, Englishman, discovered that every star's position shifts back and forth during the year by 20.5 seconds of arc, due to the Earth moving in its orbit. It's called the aberration of starlight, and it's relative to the speed of the light coming from the star. It's kind of like when you're out in the rain running to get to your car, it looks like the raindrops are slanting so as to hit you with the maximum efficiency. That's because even if they're going straight down, you're running into them. When you start here, that drop is here. When you get here, it's there, so it's closer, so your perception is that it's slanting. So the slanting of the raindrops is the same as the aberration of starlight. Now, by then, there was already a pretty good estimate of the speed of light. So we set up a triangle with the 20.5 seconds of arc is this angle. The starlight is moving towards us at 186,000 miles per second. That's a very narrow angle. This is not to scale, by the way, 20 seconds of arc. This other side of the triangle, which is the Earth's velocity in its orbit, is 18.6 miles per second, which is, 10 to the minus fourth of the speed of light. Okay? So, there it is, 20.6 or 20.5 seconds, 18.6 miles per second. That's the speed of the Earth in its orbit. Now that's an extremely important number, isn't it? That's the key to the whole thing. The Earth has to go, if you take distance equals the rate times the time, 18.6 miles per second times the number of seconds in a year converted to miles, the Earth has to go 589 million miles during the year. Remember, we know the length of the year to a second now after Tycho. So now we got the circumference of the Earth's orbit divided by 2 pi gives us the distance of 93 million miles from the Earth to the Sun. So we finally know the scale of the solar system due to the work of Bradley on the aberration of starlight. How about that? And that pretty much was the end of the geocentric theories or stationary Earth theories of the solar system. The last one is Friedrich Wilhelm Bessel, who you can see was apparently the great-great-great-grandfather of Johnny Cash. He measured the parallax of a star. He was one of the first ones to do it. He was the second one to do it, but the first one to publish, so he gets the credit. The star 61 Cygni, he determined that its distance was 11.4 light years, or he was within a few percent of that. So that was a major big deal, measuring the distance to a star outside the solar system. And we'll look at the details of that next month. So this is considered to be the beginning of modern astronomy, and by definition, the end of the study of ancient astronomy, which is what we set out to do. Okay.